Okay, welcome back. So we will start our work again. And the second talk in this session is from Professor Shuang. He's from Peking University. Today he will talk about new materials physics, design, synthesis, and characterization of new bulk quantum materials for condensed matter physics. Let's welcome.
Thanks for the organizer to give me an opportunity to introduce some result. I'm sorry, somebody always call me. Hello? 什么事儿？是 Sorry. Okay, let's go back. Some tutor want to tutor my children, so always call me. I don't know what happened. Okay, so I realize the audience is more in general, so I think maybe I should change my topic. You may notice I just give a bigger topic like a new material physics, but the main content is talking about how we try to design, synthesize, and characterization of new quantum materials for condensed matter physics. Meaning we try to grow some new compound in our lab and doing some measurement. And hopefully those compound is some exotic quantum materials. Okay. So my name is Shuang from International Center for Quantum Materials at Peking University. This is my outline. First, I give an introduction and the method, talking about how we do our research and what are we planning. So which compound we are choosing to doing some research or study and growth. And then to explain this more clearly, so I try to separate to three different research modes. Like one is a single object, meaning we know what we are going to do, so we just grow the compound and do some measurement. The example is we try to, it's close to 10 years ago, we discovered the first experimentally confirmed well-stand metal tandem arsenide. And also we also do some research, like we have some idea, like we know which compound have different crystal structure, and we try to synthesize some kind of compound with this structure. And we find some interesting physics in carbon magnet and also ferromagnetic. And the third part, we try to do something we don't know and just randomly try and have some small idea inside, and sometimes, fortunately, we can find some interesting property for new quantum materials as well. So this is, let's start. So firstly, what is a quantum material? So from the website, I checked Google and says this term is an umbrella term in condensed matter physics, meaning you can encompass all material whose essential property cannot be described in terms of semi-classical particle and low-level quantum mechanics. I think this is a very good explanation. So I think before 20 or 15 years ago, there's no such term as quantum materials. We are talking about strongly correlated physics, high temperature superconductor, topological materials, and spin glass and quantum spin liquid. And unfortunately, currently we can use a single term to cover everything, right? So what we are going to do, we try to understand the physics, and in lab we try to synthesize some compound, mostly a new compound, and we try to using those compounds, doing some measurement, try to understand some physics. Those physics including some unconventional superconductor, and some compound may have non-trivial topological state, and some compound may have a exotic magnetic ground state, like a quantum spin liquid. And also, we also have potential to find some functional materials, meaning we can use thermoelectric materials to do some energy conservation. Okay, so this is the routine or research routine in my lab. And basically, we have many different elements which are on the shelf, and we choose some exactly elements and simple compound we want, and we seal in a false envelope because usually it will react with air at high temperature. And then we'll put inside many small furnaces and large furnaces and heat up to a high temperature. So with controlling the potential of elements and the temperature and the rate of cooling. And we fortunately sometimes we have some beautiful single crystals. Of course, you still need to do some X-ray diffraction, EDS, and other measurement to confirm with the right compound on red crystal structure that you want. And finally, we have some physical property measurement systems, something commercial available, or something maybe we have to home build in our lab and do some measurement. So this is a very simple routine. But usually, one student finish the whole thing is need around like 2 weeks or 3 weeks because you need to starting from new materials and try to understand which way is better to synthesize this. Okay, so the first thing and a very important thing is you need a crystal. So why you need a crystal for quantum materials? I think because the crystal have a particular crystal structure, right, and particular electrons. So meaning you can using a quantum mechanism to understand it, and then you can predict some physical properties. And this is the most important. But at first we must have a crystal. So how to do that? It's dependent on the time or the money you want to host, right? So if you check in the cave, you find sometimes you find a very huge crystal of silicon, right? And this is the Earth's mother using like 10,000 years to go to a big crystal. But fortunately, in our lab, we don't need such big crystal. We just need a crystal like 1 centimeter or 1 millimeter, and then you can do enough measurement for most of the time. So how to grow it is a long story for short. So basically, you need some know some basic knowledge about the phase diagram. For example, if you want to grow intermetallic compound with gadolinium and antimony, you check the phase diagram and you find where is your compound. For example, you want to this compound 1,1, you notice the melting point is over 2,000, right? So it's too high. So basically, very few labs has those kind of high temperature furnaces and it costs a lot of money. So at this case, maybe you can choosing growth compound from liquid phase, meaning you starting the element completion at this point, right? Because this phase is a mix of liquid plus solid for gadolinium and antimony, right? So fortunately, if you choosing space around here and you mix the compound and cooling down at this point, some crystals of gadolinium antimony will crystallize inside, salt inside the liquid. That's what we call as a flux method. Of course, you also may notice some problems like which crucible you use to contain your compound, because sometimes at high temperature, the crucible will react with your element. And also you need to consider the vapor pressure, because antimony have a very high vapor pressure, and sometimes if the temperature is high enough, it will cause some explosion to break your course envelope. So many things you need to consider, and you ask a student to try. So try many times, and finally you hope for some opportunity, you have some crystal you want. Okay, so that's the basic ideas. And another point is how can we find this compound? So if you check in the elemental table, you find some different areas, right? This is archive earth and archive element, and this is a main element which intends to gain some electrons when they reacted with other elements. And it also has a transition metal. This usually has some magnetic properties because it has d electrons. And we also have a 12 electron compound. 14 rare earth element. Usually it's a 3 plus with 4 electron as a core share, and you can have a local moment on that. So for those different elements with different combinations, you have over 25,000 inorganic compounds in SASD database. This number is not very big, right? But you consider you may have some different pseudo alloy, and also you need to measure different properties. This is impossible that you try everything, right? Even like 1% of those compounds is enough, it's too much for people in the whole life, right? So how can we seeking available quantum materials among those so many compounds? Well, so this is my PhD advisor, Professor Paul Canfield. He worked for Ames Lab over 30 years, I guess. This is a very cool picture, I guess. Just take some compound out of the furnace. And he said this is something like you fishing in the Fermi Sea. I think it's very interesting. This is his son. His child make a cartoon for him. So posting Nature Physics. This is actually you on your boat and you try to fishing something like I guess this is some superconductor or geometric frustration or something very interesting, right? So the main point is how can you find a right place or right side to fish, right? You need to choose the right side, which has a lot of fish. Then you try to fishing, and then the opportunity to get the interesting fish is increasing, right? So you need to find the right side. So how do we find the right side? Okay, so I think briefly introduce. I think we have a different research modes, right? So everybody has a research mode. This is our research mode. So I introduce the first thing, single object, which is easy. So we know what we are doing. Somebody, like some collaborator tell me that you should grow this crystal and check what's going on. Or we check on the archive and see somebody has grown something interesting, and we just try to follow. So this is interesting. So my example is we discovered well-said metal tungsten arsenide. So this is first say as a well-said metal. So what is well-said metal? The Dirac equation describes particle, the Dirac electron, right? So if the Dirac electron has no mass, so Professor Well found that you can define the parity of that. So like you have a right-handed, meaning the spin and the momentum is parallel, or you have left-handed, meaning spin and momentum is anti-parallel. So he can write down Well equation, which is much simple, and can describe half of Dirac fermion is Well fermion because it has certain parity. So although this equation is very old, but people cannot find it in real space, right? Because if we don't have found any fermions have is massless as far as I know, right? Only boson is massless. So it hasn't been found Well fermion in real space. But find quasi-particle which can be described as in Well equation in condensed matter in solid equation is a very old idea. So this paper was published in 1983. These two people described that you can find a Well fermion in a crystal, right? So this is actually an old idea, and it will also describe you can find the Alden-Bell and Jackie anomaly. This is one of the most important chiral anomaly in high energy physics, right? But then I think it's 2007 or somehow. So some people in condensed matter rediscovered these things. Actually, because the tools to do some condensed matter calculation has been much improved. So meaning they can actually predict some materials which is really a well-set metal, meaning this compound has some band crossing point at the Boolean zone, and this band crossing point is splitting due to the spin-off coupling and breaking the time reverse symmetry or inversion symmetry. Give you some well point. And this one point, according to the topological theory, must be connected by the surface Fermi arc. Meaning, if you check the surface state of the well-set metal, you found some partial of the Fermi surface, meaning you have Fermi arc instead of a loop. So this is a very exotic feature people can imagine. So how do we, another point. So for those well-set metal, according to the high energy physics, you can soon find an ABT anomaly in well-set metal. What is that? Meaning if you apply a magnetic field and electron field to solid materials in a high enough field and beyond the quantum unit in the last Landau level, because your density state is proportional B dot G, and this is a proportional proportional conductivity, meaning you have a charge pumping effect. You apply more magnetic field, and your conductivity becomes higher. So meaning you have negative magnetic resistance, and that is a Carroll anomaly. It's a Carroll anomaly. Here, the magnetic field and the current direction is parallel. This is a high field limit, and even at a low enough magnetic field, some people also predict that you also have a negative magnetic resistance. Okay, so how can we find the well-Fermi or well-node in quantum materials? You need either breaking the time reverse symmetry, meaning you need magnetic materials, or you need breaking the inversion symmetry, meaning you have some compound with a little bit strange crystal structures. So in 2007, actually, initial prediction is some paraclide compound, the ruthenium iridium 207. But this compound is magnetic and have a very complicated magnetic domain problem. So until now, people haven't confirmed the experimental is a well-set metal. And also, other people make some suggestions for candidate, like kind of arsenide, silver to selenium. Many compounds we tried it like 7 or 10 years ago. But many compounds have some problem in the experiment. One is like the structure information is not correct, or the band structure calculation is not precise, or some compound is difficult to form a single crystal. Like this one, it has a low temperature phase, which is inversion symmetry breaking. The high temperature phase is unbreaking, a high symmetry structure. So if you cooling down to a low temperature, usually you cannot obtain the low temperature phase. So this is difficult and very annoying. Fortunately, we find this compound is more helpful to do some experiment. So this is our collaborator published a paper in 2015. It's predicted the well-set metal, and arsenide is a well-set metal. Without SOC, you find some 6 nodal line. And with SOC, we'll vaporize 6 well point. And actually, it's 2 different groups of well point, 8 on one plane and 16 on another plane. And this will show some spin texture, the opposite priority. And when we look at the compound, see what we are going to do, how to draw the crystal. You notice this compound belongs to a small group of isostructured compound. Here, the transition metal is tantalum or niobium. Both have an extremely high melting point. And the other 2 elements is phosphor and arsenic, toxic, and has an extremely low boiling point. So at this point, it is difficult. You grow the crystal just from the liquid, right? But another way is you can actually grow the crystal from chemical vapor transfer, meaning you're using some vapor of iodine or arsenic vapor to transfer the materials from the low temperature or high temperature to the other side. And at that side, it will crystallize to a small single crystal. And we did that, found that this is a very successful crystal growth. And this is the first tandem arsenide single crystal we grow. Although it's very small, but we found the mobility is extremely high. Okay, so based on our crystal, our collaborator in Princeton, Professor AHE Hassan, and his group, including Shuang, do some RPAS experiment on this compound, and it was published in 2015. And they found the well point in both states, the band crossing point, and also more important, the Fermi arc at surface. Both give solid evidence for the existence of a well-known arsenide. Another point is whether we can find this chiral anomaly in tandem arsenide. So we did some measurement, like longitudinal magnetic resistance measurement. This is a resistance versus a magnetic field. To some extent, at a certain temperature range and a certain magnetic field range, we found some negative magnetic resistance. However, we noticed the negative magnetic resistance may have different origins. For example, if your compound has a very high mobility, your current may have disturbed by the magnetic field. At that point, you also observe the negative magnetic resistance. That's what's called a current jetting effect. And also, if you have some magnetic impurity, the magnetic field may suppress may align the impurity, the moment of the impurity. So may that at that point suppress scattering of the electrons. Also give you a negative magnetic resistance. So to try to prove that what we observed is a chiral anomaly, we need to do something in experiment. So what we did, firstly, we found that this negative magnetic resistance is not dependent on the crystal orientation. It can exist in any direction, like the A-axis and the C-axis. Also, we draw a different batch of samples because the chemical vapor transfer method and the low carrier concentration. We found that different samples may have different chemical position. Chemical Fermi energy. And we measure those samples, find that some compound shows a negative magnetic resistance, and some doesn't, meaning it is strongly dependent on the position of Fermi level. And we're using the quantum oscillation of this compound to determine what is the position we have for the compound. And we collaborate with some theorists to find the chiral anomaly. It can be well understood as a Barry curvature effect, meaning actually the negative magnetic resistance is proportional to 1 over EF squared. Meaning when the Fermi energy is more close to the well point, we have a stronger chiral anomaly. When it's away from that, we almost cannot see that, like A5. This one, yeah, right. So this is some strongly evidence for that we really observe a chiral anomaly instead of a current jetting effect. Okay, we also wrote other compound like tandem phosphide. This compound has a little bit interesting because here's a well known for this compound, tandem phosphide. It's very close. You see this two petal package. The priority is opposite, like very close in the case space. Meaning, if you have a very strong magnetic field apply along this compound, you have some opportunity that for the magnetic breakdown, meaning the electron wave function will overlap for this two well pocket. At that point, because these two pockets have a different priority, when the wave function is overlapped, the only way happens is it will open a small gap. And this gap open, we have a well-known annihilation in a strong magnetic field. And indeed, we observe this situation of the field around 35 tests, 31 or 35 tests. Here we show the Hall resistance response. You see at around 31 Tesla, it has sign reversal because well-known one, this one, is an electron pocket. When it's annihilated and open a gap, the only left is some hole pairs. So that gives you a sign reversal for the Hall resistance. Okay, so this is two works we did in 7 or 8 years ago. Okay, the next part where I will talking about something we try to search in some quantum materials with a particular magnetic structures or crystal structures. This is what we very familiar in our brain. So example is discover some Kagome magnet and parallel magnet. So this is a Kagome lattice. I still remain the Chinese letter because I don't know how to type Japanese letter now on our website. So it says the kago means bamboo, right? Ni means you wave this, and you have this thing. You can find these patterns in China, in Japan, and Japanese physicist Shuang. He discovers that when you using this simple lattice, you can describe many interesting physical properties. Like you have a magnetic spin on each side, and it's strongly geometrically frustrated, and hopefully you can find a very exotic state like a quantum spin liquid or something. Also, even without magnetic ions, you still this simple structure gives you a very particular band structure. And that band structure contains a flat band and other band crossing point, meaning you can explore some exotic physical properties on this simple model. So one of the exotic properties is a chain gap opening in Kagome lattice. So what is chain gap? Chain gap means you can have a quantum anomalous fault, right? So the simplest example is if you have a topological insect, you have a surface state is a cone, and when you are breaking the time room symmetry, that will further breaks a gap. That gap is a chain gap, and you have a protected H state. And if your Fermi level is around here, you measure the Hall resistance, you find a quantum anomalous fault effect. Okay. Actually, this effect has been predicted by Hodan. I think it's a Nobel Prize paper in 1988. So you have a honeycomb lattice with a staggered magnetic interaction. You see a chain gap in Hodan model. Even without some staggered magnetic structure for a Kagome lattice in 2000, with SOC and time room symmetry breaking, you have this single band crossing. For the associated time symmetry breaking, this band crossing will open a small gap, and this gap is topological non-trivial. And you see, if the Fermi level is around here, you should see a quantum anomalous effect. So what should we do? We're motivated by this model, right? We try to find some real materials which contain Kagome lattice, and the lattice is formed by some magnetic ions. And fortunately, we may find some interesting physics. This is just a rough idea in brain. So what should we know? We expect we found some magnet which has autoplane ferromagnetic, right? This is the model suggested. And we have a pristine Kagome lattice, undisturbed. And the interlayer coupling, we prefer to be very weak, because if you have a strong weak, that becomes a three-dimensional physics instead of two-dimensional. So unfortunately, if we look around the Kagome materials, which is formed by transition metal, we find that basically they are more like a 3D, and also because the transition metal has a small anisotropy, you don't find autoplane ferromagnets. Usually the magnetism is in-plane or anti-ferromagnetic. So what should we do? We found a particular structure which can be seen as you adding 5 local moment bearing rare earths inside this well-known cobalt-tin type structure. The cobalt-tin structure, like you can see, the cobalt atoms form carbon on side, and tin atom is like this. And the rare earths, if you put them inside this space, and the pressure just push the tin atom up and down, and then you left a pristine carbon which formed by the transition metal. And because this side is bigger, the next side you cannot put another rare earth inside. So you put right out the next layer, so make your space bigger, right? So your interaction, interlayer coupling expected to be weaker, right? So this is a well-known compound, ternary compound, which is contain rare earth transition metal X, meaning tin, germanium, and other compounds. It has a large family, and the chemists call us hafnium germanium 6 iron 6 type structure, and it has a various magnetic properties, which is dependent on the rare earth, and the transition metal. So so many compound 1,6, which one we should choose to measure at first? There's some strategy to control the magnetism and the magnetic anisotropy. Basically, for rare earths, you have light rare earths and heavy rare earths. And in the general physics 101, you know Hounslow or ground state, right? Your L and S is J equal L minus S for light earth, so equals to L plus S for heavy earth, right? So the rare earth and the transition metal magnetic coupling is needed to be connected by some 5D electrons. So you have a Heisenberg exchange from 4F to 5D, and this number is negative 2J/1, meaning your S moment is coupled with 5D's S, and then you have some hybridization between 5D and 3D. So meaning if you have light earth, the J equals L minus S, this rare earth moment is parallel with your transition metal, right? I mean that is a ferromagnetic ground state. But if you are heavy rare earth, it's antiparallel, means a ferromagnetic ground state. And because because the rare earth moment is highly localized and it has some strong anisotropy, depending on the crystal electric field effect, you can expect many different anisotropies for this compound, and this anisotropy is very strong. But fortunately, we'll find one particular compound, like turbine. Due to the crystal electric field effect, the turbine moment is autoplane, point autoplane. That polarized the manganese carbonic element to the autoplane again, and this is a ferromagnetic state. And that gives you a very interesting model that we can form a chain gap carbonic magnet in experiment. So this is our compound. We grow the crystal from thin flux, and the crystal is very beautiful with hexagonal shape, and you can leave it. And this is our collaborator doing some STM and TEM measurement to confirm that actually you observe manganese-based carbonic lattice, and this is on the side way you see clear layer structure of this compound. Okay, what is our observation? So we find is easy axis the ferromagnetic state from room temperature down to 2 Kelvin, and all the manganese are pointing up and the turbine is pointing down. And the saturated magnetization equals 6 manganese minus 1 turbine, and a large cohesive field around 1 Tesla. So it's a hard magnetic. And this one magnetization you can see very clear, right? And also, more important, we measure the anomalous Hall effect. You see the Hall signal just follow the shape of the ionization, right? Meaning it's a very clear anomalous Hall effect, even down to 2 Kelvin. All right. So our collaborators doing some STM measurement on the manganese layer. The most important observation is he scanned the field and was kerneling gate voltage or something. So then he described interesting Landau-Fan diagram for a massive diaphragm, meaning this diaphragm has a small gap around 50 milli, but this gap is topological non-stability. We can using spin polarized diaphragm with a chain gap in the SOC magnetic carbonatics using this model to repeat this shape of Landau-Fan diagram, and is to obtain some parameters. The delta is 34 milli, sorry, not 50. Okay, so how to prove this delta is non-trivial, or what is the chain number of that? That needed our measurement on anomalous Hall effect. So basically, we observe a purely intrinsic anomalous Hall effect, and anomalous Hall conductivity, meaning using the resistance, anomalous Hall resistance divided by the square of the longitudinal resistance, we equals 0.14 quantum number per Cabomi layer. So what we observe is actually with our Fermi surface is below this gap, and that gives you some significant direct curvature field, but it's less than the quantum number. So this model exactly follows our measurement, indicating the chain number for this gap is equals 1. So that's a good consistent. Another measurement is the collaborator using STM using voltage. We see when the voltage around 130 milli on H, we see a clear step H state. So it's another consistency with existing chain gap because it has a topological protected H state. Okay, so what do I have? Oh. We also measure some anomalous effect. Anomalous effect means in the counterpart of the Hall effect, Nernst effect, or thermal Hall effect, right? Because for Hall effect, you have a voltage difference in this direction, and you apply a magnetic field, you see the Hall voltage. The Nernst, you apply a temperature gradient, you see a voltage difference. For thermal Hall, you apply a temperature gradient, you see a temperature gradient in the long-term space. But if you measure those things in magnetic material, you see some anomalous counterpart. Those anomalous counterpart is strongly related with some topological properties. Actually, if you understand the distribution of barrier curvature, you can calculate the anomalous Hall effect and anomalous Nernst effect theoretically, of course. So we also doing those measurements, we find a significant anomalous Nernst effect and anomalous thermal Hall effect. And those things can help us to understand the entropy and charge transport of a massive diaphragm. Okay. Okay, we also doing some measurement on other rare earth compound and find for heavier rare earths, actually you just close the chain gap. And this gap closing can be understood if you introduce some deviance factor, and this one have a different compound and different magnetic ground state. For example, the terbium one is anti-ferromagnetic, but if you apply a field, it can be polarized to ferro. At the same time, you see a spontaneous, see a anomalous effect, which is consistent with our expectation. Okay, I don't want to introduce this too much. Yeah, 20 minutes. All right. This is some new work we are doing now. So we understand this Cabomi lattice, this can give you a flat band or band crossing. So We also noticed actually you can find more interesting band structure if you consider some particular lattice. This has been explained by theorists like who know them. Tony, what do you remember the name? He said if you're using a line graph, meaning the Kagome lattice, a line graph of honeycomb lattice, and we always see this flat band. So this flat band meaning you have some quantum cancellation of the phases. So the electron, the current will just circle inside, not go out. So this is topological flat, right? So for paraquat lattice, it is a line graph of a diamond lattice. We also see a flat band, and there's a parabolic band touching on the gamma point. So this touching is a topological touching. We also see some interesting behavior. Okay, so motivated by this paraquat lattice, we also try to grow some compounds, see what's going on. So one idea is grow this rare earth iron 2 or manganese 2 compound, which the structure means Lavi phase. Yes, Lavi phase. Here the rare earth is from a diamond lattice, iron from paraquat lattice. So basically we try to see what's going on for the iron paraquat lattice. For serum iron 2, we measure the magnetization, say it's a ferromagnetic compound with TC around 220 Kelvin. And we also see a very strong anomalous effect in this compound. And this anomalous conductivity is very large, larger than other compounds as far as you know. So why it's so large? So we can compare with other compounds. You find something interesting. We compare with non-4F full shell of 4F moment, like lutetium, and the phonium has no 4F moment. And we also compare with 4F local moment, like gallium and terbium. This two is ferromagnetic. So this anomalous effect is the signal is reversed because your iron moment is inverse, right? So the interesting thing happens here. So if I plot the secondary magnetization, the x-axis and y-axis anomalous conductivity, you notice this serum has the largest anomalous conductivity, right? But the smallest secondary magnetization. Very interesting. So what's going on? We studied in our way. So we do some pseudo-alloy compound of the serum and ethylene iron. You notice these two compounds have a very small difference secondary magnetization. But the anomalous effect of serum is much higher. So with a very small amount of ethylene doping, you see a significant drop of intrinsic anomalous effect. And then for further, the magnetization increase slowly, and the anomalous effect decreases slowly as well. So this part shows the delta M versus delta anomalous conductivity. You see closely linear shape of this law. Very interesting. So how to understand it? So our collaborator do some calculation on those compounds. So you remember for a paraquat lattice, you should see this flat band with a band touching point around gamma point. However, these two compounds has a chimeral symmetry breaking because it's ferromagnetic. So this double degenerate flat band will split to upper flat band and lower flat band. Right? Unfortunately for ethylene, the Fermi level is located between them, so you cannot see too much signature of a flat band. However, for serum iron 2, because this one has one more electron than ethylene, serum 4+, ethylene 3+. So you just lift your Fermi level around the upper flat band. Here you cannot see clear about upper flat band because it's strongly hybridized with the serums of 4F electrons. And our calculation shows that actually you can see a very strong barrier curvature field and strong density state for serum. So here we have enhanced electron specificity, means the electron mass is much enhanced in serum iron 2. And also we have very large also conductivity. how to understand it. So the series through the calculation, so that actually after the hybridization, you see this flat band hybridized with F electron serum and open a small gap. This gap is a very curvature hotspot, and following the calculation, you see this gap is chain equals 2, the number equals 2, and that gives you a large amount of conductivity for this compound. Okay. All right. So I have 15 minutes, maybe 15 minutes. Okay. So I will introduce the third mode examples like unknown materials and unknown properties. Just very quickly. So this is a slide for introduce what is an anomalous effect. I guess people already know that because anomalous is proportional to the magnetization, right? But the Hall is proportional to the E field. The critical thing to understand anomalous Hall effect is try to say how the magnetization plays a role like an external magnetic field. So to understand it, actually have different mechanism of anomalous Hall effect. Like you have an intrinsic contribution, meaning your magnetization just plays a role like a pseudo magnetic field in the K space. And then you have this new chain equation. You describe the electron moving in the K space, and this E is a very curvature field. This looks like a pseudo magnetic field, external magnetic field. Give you some disturb of the motion of the electrons and give you an intrinsic contribution. This intrinsic contribution is independent with your electron lifetime. So the anomalous Hall conductivity is a constant. The other two mechanism is extrinsic mechanism, meaning it is dependent on the scattering of the magnetic impurity. So at that side, for smooth scattering, it is proportional to the electron's lifetime. So the anomalous Hall resistance is proportional to the resistance. Okay, so the anomalous Hall effect is important. Because we can use that to describe the curvature field, which is a crucial language for describe the topological properties, topological band surface. Okay, so what we are trying to do from zero. So we look around those compounds like a topological magnet. We notice that the anomalous Hall effect is actually not too big, particularly for the anomalous Hall angle, which is defined as anomalous Hall conductivity divided by the anomalous Hall conductivity. That meaning how much electron current will projected to the transversal direction, right? It's only 20%, meaning you have a 20% of current on that direction. And also the anomalous Nernst effect, meaning if you apply a voltage, you apply temperature gradient like 1 Kelvin, and then you only obtain like a 10 microvolts difference on the transversal side. So our motivation is try to just look around, see what can we have. What we choose in the materials is something called the heavy fermion materials, right? It can be described as conductivity. This is one of the classical strongly correlated material systems, and it is known in every textbook, right? Because if you have a 4f and 5f electrons, and those electrons, for particular element, those 4f, 5 orbitals very close to the Fermi level, meaning the electrons have some opportunity to give you a pseudo singulate state at low temperatures, because it intends to form some singulates. Electron move in the lattice very slow. Because it's very slow, so you look at the kinetic energy is very small, and also the electron looks very heavy. So meaning it has a heavy electron mass, and that meaning it is a heavy fermion. On the other hand, so if you try to explain it in the momentum space, it's like the hybridization between the F electron and the conduction electron give you a very narrow band. The narrow band is so flat that the kinetic energy is small. And at that time, the polar interaction is important, and so you can see some interesting unconventional physical properties related to the strongly correlation, right, like a heavy fermion superconductor. So what we are going to do, we want to see whether this strongly correlated material system can give us some important topological property, like a very large anomalous effect or large Nernst effect. So if we check this idea, think it's fancy, but unfortunately we discover that after 30 or 40, before 30 or 40 years, people already think about it. So they said that in heavy fermion compound like conductivity, a through scattering mechanism dominates, and the anomalous effect is small, unfortunately. However, if we look at this theory, find is particular on some ferromagnetic hairframe, meaning the moment has not magnetic origin, right? If it has magnetic origin, it's breaking a temporal symmetry. So that at that point, it can be explained by the band theory. So we think we saw maybe in ferromagnetic conductivities, there's something maybe different. So we are looking at ferromagnetic strongly correlated system, see whether we can find a large intrinsic anomalous effect. So there's some theory, I just briefly introduced. Some paper haven't been published, but posted in arXiv. This compound is a serum-based compound with a cobalt, the 1,2,2 structure, like the iron-based superconductor. The only difference is the cobalt has a net magnetic moment, meaning has an adherent ferromagnetism, and its EC is around 200 Kelvin. The lanthanum has no 4f electrons. You see the magnetism is purely from the cobalt compound. And if we have a 4f1 like serum in this compound 122, we find the TC is very close to the lanthanum compound. And the saturated magnetization is close to this lanthanum compound as well, meaning this difference is much smaller than the punctual ground states of serum 4f1 electron configuration, meaning the serum 4f1 has been purely or nearly perfectly condo screening, so by the conduction electron. So you cannot see the local moment of the serum moment. So we're doing some Hall effect measurement. We find the anomalous conductivity. It is 10 times larger than the lanthanum compound. And our collaborator do some band structure calculation and show this. We find a topological non-ring band structure in serum cobalt-2, arsenic-2. So next, they want to test this topological non-ring is a condo effect induced topological non-ring, meaning it's starting from a strong correlated electron. So what is the picture? The picture is at the high temperature, the F electron and the conduction electron is decoupled. But at a low temperature, it forms a condo lattice, meaning in the K space, it forms a very narrow band near the Fermi surface. For this compound, it forms a narrow topological non-ring, and this topological non-ring has a significant strong battery culture field that gives you a large intrinsic anomalous effect. So this is an APAS measurement and give you some evidence that they observe the topological non-ring for this compound. This is a measurement at different temperature. At high temperature and low temperature, you see the 4f electron spectrum weight is much enhanced at low temperature. This is a signature of a condo effect because the condo effect is a crossover from local moment to itinerant moment down to the lowest temperature. Okay, so we also make this such kind of a law. Say we increasing of X serum composition. It's starting from a regular ferromagnet from lanthanum 122 to serum 122. Here, serum, you see the resistance. Here, log T behavior, which is a signature of the condo lattice, and it drops down when it starts to coherent below the coherent temperature. Okay. Also, we have a enhanced electron specific heat with the increasing of the field, and we also ask the collaborator to calculate barrier curvature field for lanthanum and cerium compound. This is consistent with the experimental result. Okay, we also have some other examples, like just trying to look around, see whether we have some ferromagnetic or condo lattice, and we pick up the crystal and do some measurement, ask the student to do that. Fortunately, we found another example. This is a cerium, chromium, germanium 3. Here, the germanium also has some magnetic moment. And see the lanthanum and germanium both have a TC around 80 Kelvin. And the cerium compound has a clear low T behavior, meaning its condo effect plays an important role. Also, the large enhanced gamma ray. And what we found is although this two compound has a very similar secondary magnetization, the anomalous effect for cerium compounds is over 100 times larger than the lanthanum compound here. And we plot this anomalous conductivity, but basically it is intrinsic one, and also the anomalous angle and anomalous conductivity give a red position for this compound, which is even larger than most of the compound we know, as far as we know. More important, we also measure the Nernst effect, and this Nernst effect is as large as 10 microvolt per Kelvin. Okay, this number is still small, but if you compare with other compounds, you find it's ranked the second for the all known compound, like at this position. The first one here is a uranium-based compound. Interesting because it has 5 electrons. Here we have 4 electrons, and indicating the electron has some opportunity to strongly enhance its anomalous effect and Nernst effect. Okay, our collaborators also do some band structures for calculation for lanthanum and chromium. So basically, this is DFT, right? So not DMFT. But still, you can find some signatures of active electrons. For cerium, you see a very strong distribution of the white band, right, on top. So we have a significant F band near the Fermi level. And also, we calculate the barrier curvature field in cerium, and we see the number is close. Of course, you don't expect a very precise calculation because strongly correlated is difficult. But anyway, it can be some indication. For lanthanum, I didn't show here, but the number is below 100, so it's consistent with our measurement. So I think I had 3 minutes. Okay, I think I have finished this. We don't need even talk to the last one. Just I see. Okay, so I give my summarize and outlook. Synthesize new quantum material. I guess it is too broad, but actually you know what I'm doing currently. So we just get some idea in brain. Sometimes the compound is predicted, sometimes unpredicted, or we just try to find some isostructure compound, or look around to see whether the database has something exactly what we want, depending on the crystal structure, particular physical properties of our element composition. So then when we synthesize that, and for over 90% chance we lost the game, so this is some trivial compound. But over 1 year or 2 months, some lucky student may find some interesting compound, and we can publish some paper. So that's the game we are playing. So I will say there's more properties we can still measure, like 20 years ago, we are focused on like a resistance, quantum critical point for the heavy fermions or etc., something like that. And currently, we can measure the Hall effect and Nernst effect and thermal Hall effect and discover something new like the topology related with strongly correlation or something. I guess in the future, we can discover more interesting compound. So this is acknowledge. Thank you for my student collaborations. Yeah. Thank you for your attention.
Thank you very much for the wonderful talk. Is there any questions? Okay, may I ask a short question? So for the second part, you introduced a Kagome material, right? So this Kagome material is also a layered compound. And if you look at the different layers, it's like a ferromagnetic, right? Okay, so do you think this material has some advantage over the MonBD 124 material? Because that one is for different layers anti-ferromagnetic.
I see. I think it's not good as manganese MBT because MBT is a real layer compound. So between layer to layer, you have van der Waals interaction. So meaning if you want to layer it, you just it's much easier. And also you use MBE or something to synthesize a thin layer is much easier. For those compounds, although it looks like a layer, but actually it has some strong bonding between the layer, right? Strong bonding between the layers. So at this point, it's very difficult to really obtain a single layer. So yeah. So if you really obtain a single layer of the compound, like you're using MBT, with control of the chemical potential, you may have some chance of obtaining anomalous effect. But currently, I don't think we have some idea to finish this. So I achieve it. Yeah.
Okay, and actually, you have already measured the Hall conductance for that material, right? So is it get a quantized value or not for the Kagome material?
You mean the quantized?
Yeah, it is quantized.
Currently, our Fermi energy is below the gap. So away from the gap, around 130 millieV. So this at that position, the barrier curvature field is weaker than in the gap.
Yes.
In the gap, you see a quantized number, but here you only see 0.14.
Yes, but if you add some gate, can you shift the gating? Yeah, can you shift the Fermi level to a upper one?
This is a metallic compound, so you cannot.
Oh, I see.
Yeah,
I see. Okay, thank you very much.
You're welcome.
And any other questions? Okay, if not, let's thank Professor Jia again.